Howdy. Now we're still talking about the physical properties of water, and we're going to be introducing here and explaining later the hydrophobic effect. The hydrophobic effect is best understood when you think of those oil droplets coalescing in water. And you need to think about it from the point of view of the water molecules, which vastly outnumber the oil molecules. Okay, so you're the water, the oil is trying to escape the water. Okay, now if you think about it that way, a nonpolar molecule like oil is going to minimize its surface area to the water by coming together. And by doing that, it's going to organize fewer water molecules around itself than if you had separate droplets organizing lots more water around itself. And so that's what we mean when we say that the oil droplets cannot interact with the water. They have no groups with good hydrogen bond donors or acceptors, and they're certainly not charged. So they can't form any favorable interactions with the water molecule itself. And so they crowd together, being pushed away from the water so that the water is minimally interfered with. Okay, so why are we interfering with the water? Because the water is going to surround the oil droplet with the minimal surface area and organize its own hydrogen bond donors and acceptors to optimize that space for the oil, right? And once you organize one shell like that, that orients all of the neighboring waters to make a second shell and a third shell, and there's a term for this. It's called clathrate, which comes from the Greek cages. And we don't want to form a bunch of cages around a bunch of separate water molecules. That's very expensive entropically. We'll talk more about entropy in an upcoming video, but suffice it to say, the waters that are held in place by these cages or clathrates are not sampling as many possible conformations and are therefore energetically paying an energetic price. Okay, so it's expensive to organize water around lots of separate droplets. It's less expensive to organize them around one coalesced droplet of all of the oil. Okay, so that's what this slide is talking about. It's talking about the organizing the hydrogen bond network of water into this trapped orientation. That's not energetically favored. Okay, so it's going to minimize the amount of trapped water by pushing all of those oil droplets together, so it only has one oil droplet, larger oil droplet, but you still have to organize fewer water molecules. Okay, those are the clathrates that are organized shell after shell after shell around the nonpolar group. Okay, so that's why you need to think of it from the point of view of the water, because if the nonpolar parts of the solute, the oil, are not attracted to each other. Yes, they may have some van der Waals interactions that are beneficial when they come together as an oil droplet, but they're very minimal compared to the number of hydrogen bonds that they freeze in place. Okay, so really it is the overwhelming energetic cost of organizing water that pushes these droplets of oil together. That's the hydrophobic effect. Okay, so in other words, the nonpolar molecules aggregate. Aggregate is just a fancy word for clustering together, not through cohesion to each other, but in order to free many more molecules of water, increasing their entropy, which is favorable, more degrees of motion, without losing any of the enthalpy. In other words, any of the favorable hydrogen bonds that water makes with other water molecules. Okay, so those are still in place, but they're no longer frozen. So it's that motion that wins out in the hydrophobic effect. All right, we'll come back to the hydrophobic effect many times throughout the semester, but this is our introduction to it on this part here at the beginning. To illustrate the hydrophobic effect, we have two beakers. Okay, we have a beaker of nonpolar solutes. You can think of them as oil, although oil would float. And they're surrounded by they're kind of olive color and shape, and they're surrounded by a darker blue, and those are your clathrates, or your cages of water. Okay, so A is the starting point, and B is the final point. So we're going from A to B. Okay, and when you're in B, you have all of those non-polar solute olives clustered together in an aggregate, and you have that blue, darker blue clathrates around it, which is less of the volume. Of course, this would be three-dimensional than the individual blue, darker blue clathrates over here. Okay, so that tells you that you have less organized water in B than you do in A. Okay, so it turns out that, and we haven't really talked about this in great depth yet, but we will soon, the energetic is favorable to go from A to B. Okay, because going from B to A would cause you to have to organize more water, and that's energetically expensive. Okay, so that's just one example of the hydrophobic effect. We'll see lots of other examples as we move through biomolecules this semester. Now, there are some solutes, that is, molecules suspended in water, that have both nonpolar parts to the molecule and polar parts. And then I mentioned this when we outlined this section of the module at the beginning of the first video. And those are amphiphilic molecules, or amphipathic. Amphi meaning partial, so it could be partially water loving and partially water hating. Philic would be love, and pathic would be hate, right? Okay, so amphiphilic and amphipathic are the synonymous terms for the same thing. There's something that has a hydrophobic or nonpolar part of the molecule and a hydrophilic part of the molecule. In this example, my hydrophilic part is positively charged, but you could have something that's negatively charged, or you could have something that's nonpolar, that's not charged, right? It just has partial charges. Okay. Oops. So those are all examples of amphiphilic or amphipathic, hydrophobic. Okay, hydrophobic tails and charged or polar head groups, circled parts. All right, these actually organize in a very specific structure, and we can take advantage of the fact that amphipathic molecules organize in a specific structure, and you do this every day. Every time you wash your hands, you're using a soap, and soap is this molecule right here. It has a hydrophobic or nonpolar tail group, which likes to be buried in the dirt, which is typically oily, and a hydrophilic head group. Usually with soap, it's negatively charged, because soap is either a group like this or a group like this. So usually it's negatively charged head group. And that causes these amphiphilic molecules to organize into spheres that contain the oily dirt in the middle. So the tails are in the middle and the head groups are on the outside. Fatty acids are a good example. They also have this same structure as soap. And their sodium salts keep them soluble in water. And so we'll have a look at the different structures that these amphiphilic or amphipathic molecules can form. First, let's look at the structure of an example amphiphiles, a fatty acid. Fatty acids are components of lipids, which we'll talk about as we go farther along in the semester. But let's introduce them here because they're such a great example of what we were talking about on the last slide, an amphipathic or amphiphilic molecule. You can see the nonpolar tail is methylene groups. Of course, this should be CH3 for those of you who are paying attention for the last one. And all of these methylene groups, CH2, CH2, etc., are nonpolar. They don't have anything to interact with water, so they won't form any favorable interactions with water. They are hydrophobic, and they want to hide away from water. However, on the other end of the molecule, you see this group, a carboxylate ion, which is shown in its resonance form, but it's known to you like this, typically. And these are deprotonated and ionized with a negative charge in most biological systems. Okay, and there's that tail. So this is the hydrophobic tail, and this is the negatively charged head group. Now, the sodium is shown here as a counter ion because whenever you have these fatty acids, either in the lab or in the cell, they tend to be neutralized by a sodium ion. But those, of course, dissociate immediately when you add them to water, and the nonpolar tails hide away from each other by aggregation or assembly together of lots of these, so times 1,000 or so. They will form these structures that can trap dirt, and that's why when you use soap, the old-fashioned soaps are actually fatty acids. Okay, so when you are using soap, the soap inside water, so water is your solvent on the outside, interacting with those head groups, which are now shown as blue spheres. So these would be the blue sphere would be the negatively charged group on our last slide, the carboxylate group, okay? Or it could be a sulfate if it's, a sulfate soap. And then those gray squiggles that you see going toward the middle of this sphere, these squiggles in here, those are the nonpolar tails. Now, there's no water on the inside, okay? This is not a vacuum. There's no space, so this is full on the inside. What's in this place is probably dirt because you're washing your hands with micelles. The micelles are the soap molecules organizing together around your oily dirt, which would be in the center of this micelle. Okay, so micelles are like taking a single layer of your fatty acids, which I'm drawing schematically like this here, and then wrapping them around into a sphere. Okay, so you would wrap these around a single monolayer wrapped around into a sphere. The reason that I describe it that way is because the other way that amphiphiles can organize, if they have two tails, is as a bilayer. Okay, so a micelle is actually a monolayer and has no lumen. Lumen is the inside, aqueous inside. It's hydrophobic in the middle, hydrophobic inside a micelle. Oops. Micelle. Okay? Hydrophobic inside the micelle. That's important. That's where the dirt goes. When you have two tails instead of just one, you've got your same type of head group, polar head group. Again, this could be plus or minus charged, or it could just be a partial positive and partial negative charge. And now you have two tails. Now the shape is slightly different. Instead of having a large head group with a skinny tail, which is the shape that the fatty acids form a micelle through a monolayer, you actually stack side by side in one monolayer, and then another monolayer assembles tail to tail with the first monolayer. And in that way, you can see how forming this bilayer hides all of the non-polar tails away from the water because they're hydrophobic. They fear the water, right? And all of the polar head groups, we call them head groups, the blue spheres, are interacting favorably with water, okay? So the hydrocarbon tails listed here are hiding from the water. Of course, the edges here would be wrapped around. There would be no edges exposed to water. So in a way, if you're looking at the membrane of a cell, it would wrap around the entire cell, right? This would be the cell. So there would be no edges to these membranes exposed to water. But in a bilayer, you have this sandwich of tails in the middle and head groups on the inside of the cell and on the outside of the cell, okay? So keep in mind these definitions of bilayer and micellar monolayer with no lumen, because this is going to come up again and again. And it really is the secret to life, because without membranes, we wouldn't be able to hold our DNA in to replicate our cells or ourselves. So membranes, and we'll talk a lot more about intracellular membranes that form organelles as well, but not now. For now, we are going to finish up the physical properties of water, and the last part of this, part 2 of module 1, has to do with the way that solvents and solutes move down their concentration gradient. So we're going to start with osmosis and osmotic pressure. Osmosis is the diffusion of the solvent, okay? And what we're talking about with osmosis is the propensity for molecules to move from high concentration to low concentration. And in this case, we're looking at a glass tube with a water permeable membrane at the bottom. So the little disc at the bottom of this straw, you can think of it as a straw, has a semi-permeable membrane. We can purchase this type of dialysis straw from a vendor. And inside the straw, above the permeable membrane, is a purple solution with dark purple solutes, okay? And it's concentrated in those solutes. So there's a high concentration of solutes, which means that the water molecules have to share the space with the solute, okay? And that means there are fewer water molecules in the purple region than there are in pure water, which would be the blue region. So this region is going to be 55.5 molar water, whereas inside the concentrated solution, you're going to have less than 55.5 molar. Okay? Less than 55.5 molar water inside. Okay, so what that means is the water is going to want to rush in to the straw through that water permeable membrane to try to equalize the concentration of water outside the tube and inside the tube. And the osmotic pressure of your concentrated solution is the amount of pressure that you need to apply, here using a piston, to reduce the volume of this mixture in B. Now we want to reduce this increased volume due to osmosis back to its original volume. And that requires work, because osmosis is energetically favorable. Rushing from your high concentration of water to your lower concentration of water is energetically favored, so you need to use work to counter that energetically favored osmosis. And the amount of work is equal to the osmotic pressure. Okay? So when the solvent is moving down its concentration gradient, as shown in this slide, we call that osmosis. And I highlight that because when we're talking about dialysis, it's actually the movement of solutes, okay? So the concept is the same. We're going to be moving something down its concentration gradient, but in this case, instead of having the solvent, water in our last example, we're talking about the movement of the solute, the thing that's dissolved in water. And so in this example, we're looking at dialysis of a small molecule, which is the dark brown dot, which is captured together with a larger purple molecule in a dialysis bag. The dialysis bag is usually made of the same semi-permeable membrane material that was at the bottom of the straw in the last slide. But you can choose dialysis bags with different sized pores in them. All of them are very, very small pores, but you want to, of course, keep the goods inside the dialysis bag. The purple is what we want to keep, but the impurity that we want to get rid of, the dark brown, is what's going to move down its concentration gradient from high concentration inside the dialysis bag to low concentration outside the dialysis bag. So here we have water again out here, and this time we're going to be talking about the movement of these high concentration of brown things outward. So we picked a dialysis tubing that has a molecular weight cutoff that's large enough to allow the brown contaminant to come out, but not so large that we'll lose our precious purple molecule. Okay. All right. So at equilibrium, usually after at least 2 hours of stir, we have a little stir bar in here usually that's actually stirring the water solution, and our contaminant comes out, and after several hours we can then equilibrate the amount of solute across that membrane. And you can see now that there's just as much solute per volume in the water as there is in the bag, right? And if you want to get rid of all of it, we would have to do a third or fourth step, starting again with the pure water. And that's an important step in purification of biomolecules. And usually what we're removing is salt. Okay, so you'll see this again as we move forward throughout the semester and we apply some techniques. You'll need to know what dialysis is. So if you want to use your compare and contrast skills, I would use it to compare and contrast osmosis and dialysis. They share a lot in common. The principles are the same, but what's moving down its concentration gradient is different. In osmosis, it's the solvent, the water, and in dialysis, it's the solute, the brown thing, usually salt. All right, so then we have the chemical properties of water is the next part, and we'll start the next video for this section on chemical properties.